Okay, next we're going to look at an example of a linear system with three equations in the three variables, x, y, and z. You can see them right here. And we're going to solve this using a systematic method that's you'll often hear people refer to it as row reduction. And what we're going to use is a tool that's referred to as an augmented matrix. And what an augmented matrix does is it just looks at the crucial aspects of the system. Let me give you something to think about. If I were to go back to this example that we solved here, where we had x minus y is equal to 1 and 2x plus y is equal to 6. What if instead of x and y, I changed the variables to u and v? So the first equation was u minus v is equal to 1, and the second equation was 2u plus v is equal to 6. So I just changed the x to a u and I changed the y to a v. Well, what would change? Well, this work, I'd have to change all the symbols in this work to reflect all that, but the work would look the same, right? And of course, I'd have to change the way I express the solution. I'd have to basically just replace x everywhere with a u and replace a y everywhere with a v. But nothing else about the format of my work wouldn't change and the substance of it wouldn't change. So if you change the names of the variables, you're not really changing the essence of the linear system. So that's something we're taking advantage of here. So that what really matters here is the coefficients of each variable and the constant terms. And that's what the augmented matrix keeps track of. So that's what I'm about to introduce down below. So if the meaning of that isn't clear at this point, it will be momentarily. So here's an example. We've got three equations in the variables x, y, and z, and all three of those equations are linear. So an augmented matrix looks like this. It's a two-dimensional array, or a box of numbers, however you prefer to think about it, and I just do it this way. So the coefficient of x in the first equation is a 1, and let's just look at the first equation. So the coefficient of y is also a 1. The coefficient of z is a 2, and the constant term is a 9. So notice I'm just writing those numbers down and I'm ignoring everything else temporarily. Then for the second equation, the coefficients of x, y, and z are 2, 4, negative 3, and then the constant term is 1. Then for the third equation, the coefficients are 3, 6, and negative 5, and then the constant term is 0. Notice that I'm going quickly because right off the bat I checked that the variables are lined up nicely, so I can just copy the coefficients straight across in the constant terms. If the variables were all mixed up here, I'd have to sort them out first before I could just copy the coefficients down into my augmented matrix. So let me go back up and just draw a little arrow. So an augmented matrix is one of these. Okay, it's just a box, a rectangular array or a two-dimensional array that contains all the coefficients of a linear system as well as the constant terms. Okay, and one modification, the textbook that we're following doesn't do this, but a lot of textbooks do, and some people do this and some people don't. I really, really like to do this. I find it makes things so much easier to read. Is I like to just draw a line down here. Draw a line there just to indicate, to draw attention to the fact that here are the coefficients on this side, and here are the constant terms on this side. So you can think of this vertical line, it kind of lines up with where the equal signs are. It really just draws attention to the fact that, hey, this is the augmented matrix of a linear system, and these are the constant terms. And then right away, it allows me to say, okay, I can see that there's three equations because there's three horizontal rows, and there's three variables because there's three vertical columns. Okay, so that's an augmented matrix. So let's look at what we can do to simplify this. And I would like to just go back momentarily to this comment here, where we said that if two linear systems have the same solution set, they're said to be equivalent. So what we're going to try to do is we're going to try to continually simplify this augmented matrix until it gets simpler and simpler. But the idea is the steps that we do are not going to change the underlying solution set, so that when we do get to a very simple form, we can trust that the solutions that we come up with will genuinely be solutions to the original linear system. Okay, so enough talking about it. Let's just actually do it. So what I'm going to do is I'm going to do something that is referred to as a row operation. So what I'm going to do is I'm going to take row 2 and I'm going to change it. What I'm going to do is I'm actually going to subtract row 1 from row 2, and not only that, I'm going to do it twice. So here's the notation I'm going to use to express that. I'm going to take row 2 and replace it with row 2 minus 2 row 1. And then what I'm also going to do, so that's going to change row 2. You can see right away, this highlights the fact that row 2 is the one that's changing. And then I'm also going to change row 3. And in particular, what I'm going to do is I'm going to subtract row 1 from it, but I'm going to do it 3 times. And so the row operation is going to look like this. So it's going to be row 3 is replaced with row 3 minus 3 row 1. Now you might be wondering, well, why am I choosing to do this? And I don't want you to worry about that too much for the moment. In the next section, we're going to go through this systematically and look at the thought process behind every row operation that's chosen. But for now, just try to make sure you're following the row operations. And I want you to just give you an idea of the overall process. Okay, so I can tell you why, roughly speaking, why I chose these row operations. What I would like to do is I would like to turn both of these entries into zeros. And why is that? Why do I want to do that? Well, it's tough to answer completely right now, and I don't want to get sidetracked too much, but I'll just roughly speaking, it's just because I want to introduce zeros there, and zeros are simpler in some sense. Okay, so let's look at what would happen if we do that. Okay, so we're going to have a new copy of this augmented matrix, and row 1 is going to be the same, right? Row 1 didn't change. So we can copy that one exactly right off the bat. Okay, so now what we're going to do is we're going to do this operation. So row 2 is going to have row 1 subtracted from it twice. So, okay, that means you're going to take this row, which is row 1, and we're going to subtract it from row 2 twice. Okay, so start with these entries. What happens if I take 1 and subtract it from 2 twice? I'm going to get 0. What happens if I take 4 and I subtract 1 twice? Well, I'm going to get 4 minus 2, which is 2. If I take negative 3 and I subtract 2 twice, I'll end up with negative 7. And then if I take 1 and I subtract 9 twice, that's really 1 minus 18. So that'll be negative 17. And that takes care of the second row. So this row operation has been completed. Now we're going to perform this row operation. So we're going to take row 1 and subtract it from row 3 times. Okay, so what happens in the first column? We've got 3 minus 1 3 times. So you have 3 minus 3, which is 0. And then for the second entry, we're going to have 6 minus 3 times 1. So that's going to be 6 minus 3. It's going to give us a 3. And then we're going to have a negative 5 minus 3 times 2. So that's going to be negative 5 minus 6, which is negative 11. And then here we're going to have 0 minus 3 times 9. So that's like 0 minus 27. So we'll have negative 27. Okay, so that is an example of some elementary row operations. So the idea is we started with a linear system and we wrote down its augmented matrix. We did some row operations. They're actually called elementary row operations. We'll formally introduce those after this example. And that gave us this linear system. The idea is that gave us this augmented matrix. But behind every augmented matrix is a linear system, right? I could convert this augmented matrix back into a linear system, just like I converted this linear system into an augmented matrix, just go the other way. And the idea is those two linear systems would be equivalent in the sense that their solution sets are identical. But we're not going to stop here. We're going to continually do row operations until it gets simpler and simpler and simpler, until eventually the solution is just immediate. And that's the strategy. Okay, so like I said earlier, don't worry too much about how I'm choosing the row operations that I do. Just focus on making sure you can actually follow the steps.